أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. I am Faisal. The topic of my presentation is spin crossover, and subject which we study is symmetry and magnetochemistry. The key points of today's lecture is the phenomena of spin crossover on complexes, the factors which affect the phenomena of spin crossover on metal complexes, and then we study the applications, and last we have some question. In this slide we study the phenomena of spin crossover on metal complexes. The phenomena of spin crossover occur in some metal complexes, not all the complexes. Spin state of a complex changed due to an external stimulus. The stimulus may be temperature and pressure. Spin crossover phenomena, sometimes called spin transition or spin equilibrium behavior. The change in spin state usually involves between the interchange of low spin and high spin complexes and the pairing energy represented as a P. Here del V is represented as crystal field splitting energy and P, which is the binding energy. In high spin complexes, del V means crystal field splitting energy is less than the pairing energy. In high spin complexes, we commonly use weak ligands. Due to these weak ligands, the crystal field separating energy is less as compared to the pairing energy. And in low spin complexes, the crystal field separating energy del naught is greater than the pairing energy. In low spin complexes, we commonly use strong ligands. Due to these ligands, the pairing binding crystal field separating energy is greater as compared to the pairing energy. When the difference between crystal field separating energy and pairing energy is very small, then this phenomena then also occurs. This slide shows the phenomena of crystal field separating energy in the high spin complexes and the low spin complexes of octahedral ligand field separating for D5 case. In this diagram, we says that in high spin complexes there is a less distance, means del V is not greater between the T2G and EG states. But in low spin complexes there is a great distance as compared to the high spin complexes between the T2G and EG. In high spin complexes we use weak ligands as compared to the low spin complexes in which we use a strong ligands. When we use strong ligands, the repulsion between the metals and ligands is greater. That's why the splitting bonding energy is greater in the low spin complexes as compared to the high spin complexes. In high spin complexes, we use a weak ligand and there is a less force of repulsion between the weak ligands and the metal complexes. In this slide, we study the curves for spin transition complexes. There are three main curves. A is a gradual transition, and B is a abrupt with hysteresis loop, and C is the two-step transition. These curves are in these curves we take temperature on x-axis and the high spin molar friction on the y-axis. These curves show us how the effect of stimulus change the complex from low spin state to high spin state. In three curves, the external stimulus is a temperature. As a temperature changes, the state of a complex is also changed, and it is converted from low spin complex to higher spin complex. Uh, the explanation of this graph is on the next slide. The phenomena of spin crossover complexes is shown by the first row of the transition metal complexes, which has configuration from D4 to D7 electron. It is also occur in an octahedral ligand geometry. In the previous slide, we have discussed that the curve is plotted between the high spin molar friction and temperature. For gradual spin transition, it is followed by an abrupt change, and temperature is equal to 10 Kelvin. This is due to transition with hysteresis loop. In the gradual transition curve, we take a temperature on x-axis and molar fraction, high spin molar fraction on a y-axis. As the temperature increases, the spin state of the complex changes, means low spin complex is changed into a high spin complexes. Second graph is about the abrupt with hysteresis. In this graph, we show the two lines. First is a high spin complex is converted into the low spin complexes as temperature increase, and second is the low spin complex is converted into the high spin complexes, means the spin state of both these complexes are interchanged. The abruptness with hysteresis indicates communication between the neighboring metal complexes. In that case, material is a bistable and can exist in the two different spin states with a different range of external stimuli such as temperature in this case. For the two phenomena in which low spin complex is changed into the high spin complex and the high spin complex is changed into the low spin complex. This slide is related to the previous slides. In two-step transition, the two-step transition is relatively rare but is observed in dinuclear spin crossover complexes, for which the spin transition in one metal center renders the transition in the second metal center less favorable. In chorus, we say that the spin crossover change due to the communication between the neighboring metal complexes in the two-step transition. Then we study the types of spin crossover complexes. There are three main types. First one is a light induced excited spin state trapping, which is abbreviated as LIESST, and second is the ligand driven light induced spin change, LDLISC, and third one is the charge transfer induced spin transition. The first type is a light induced excited spin state trapping. It is due to the presence of the light stimulus. Due to the light, the spin state of a complex is changed. In the second ligand driven light induced spin change, the light changes the ligands and then the phenomena of spin crossover is taken place. And third one is the charge transfer induced spin transition. It is due to the transfer of charge between the metal to ligands, ligands to metal, and metal to metal. All these phenomena carries the phenomena of spin crossover. In this slide, we study the history of spin crossover complexes. Spin crossover complexes was first observed in 1931 by Combe and its colleagues. Magnetic behavior for the complex like tris NN dialkyl carbamato iron 3 complexes. The spin state of these complexes were sensitive to the nature of the amine substituents. It means that these are the very sensitive. If we use other complex other than ammonia, then the nature of this complex will be changed. In the 1960, the first cobalt 2 spin crossover complex was reported. Magnetic measurement and Mozart spectroscopic studies established the nature of the spin transition in atom 3 spin crossover complexes. Building on these early studies, there is now interest in application of spin crossover complex in electronics and optical display. In this slide, we study the characterization tools for the spin crossover complexes. The complex which has a low spin state has a less magnetic properties, and the complexes which has a high spin state has a more magnetic properties. The magnetic susceptibilities is key to characterization of the spin crossover compounds. The magnetic susceptibilities as a function of temperature. There are several techniques which we are used to study the phenomena of spin crossover complexes. These are the FTIR Fourier transform infrared spectroscopy, Raman spectroscopy, XRD, and UV visible spectroscopy. In this slide, we study the phenomena of spin crossover of iron complexes. This complex is the example of light induced spin crossover. In light induced spin crossover, we use a light to change the spin state of complexes from high spin complexes to low spin complexes, or a low spin complexes to the high spin complexes. In this structure, we see that in the presence of light, means photon, the bond length between the iron and nitrogen is 219.5 picometers, and on the right side of the arrow, the bond length between the iron and nickel is 200.5 picometer. It means then on the absorption of the light, the bond length may change. The state of the complex may also change from low spin to high spin, or high spin to low spin complex, but the charge on these two structures is plus 2, means charge does not change as we change the spin state of the complexes. In this slide, we see the graph of magnetic susceptibilities. In this graph, in this figure, we take a temperature on x-axis and the magnetic susceptibilities on the y-axis. At initial temperature, means at 100 Kelvin, the complex has low spin state. As temperature is increased and reach up to the 180 Kelvin, then it is changed into the high spin complexes. In this slide, we study the Masbar spectrum on the iron complexes, which has in three forms: Fe plus 2 in low spin complex, Fe2 in high spin complex, and Fe3 in less spin complex. The red lines in this graph shows the properties of the low spin complex of iron 2, and the blue line shows the graph of the high spin complex of iron 2, and the green line in this graph shows the spin crossover phenomena of iron 3 complexes. This slide shows the image of the Raman spectra for iron complexes in low spin state and high spin state. In low spin state, we see in the figure that there is a temperature 100 Kelvin, and the frequency in the low spin complexes is 2114, but in the high spin complexes the temperature is 300 Kelvin and the frequency is 2070. In this slide, we study the IR absorption of the cyanide stretching vibrations. It is a complex of iron with cyanide at the different temperatures in cooling mode A and B heating mode. Yani in figure A there is a cooling mode, and in figure B there is a heating mode of this phenomena. and we see the graph on this slide on heating mode and on the cooling mode of IR spectrum. In this slide we have some question. Question 1. Write the factors which affect the phenomena of crossover complexes. And question 2 is the write the difference between the high spin and low spin complexes.